There's a phase of matter that responds to vibration, magnetic fields, and electric fields. In that phase, alignment changes how light travels and how structure reorganizes. And the strange part is not that it exists. The strange part is that it shows up in your body. Liquid crystals are seen in cell membranes, collagen-rich connective tissue, tightly packed DNA, and fibers of the cytoskeleton. In this video, we will explore an intermediate state of matter that is neither solid nor liquid, neither rigid nor chaotic, and why that changes everything. But before we talk about liquid crystals, it will be helpful to touch on what the word crystal actually means. In physics and material science, a crystal is defined by order. It's a material whose atoms or molecules arrange themselves in a repeating pattern that extends across space. That repeating lattice structure gives crystals certain properties that are not obvious from the ingredients alone. One of the most important is something called anisotropy. Anisotropy simply means that the material behaves differently depending on direction. If you push on it from one axis, it may respond differently than if you push on it from another. If light passes through it one way, it may split or slow differently than if it passes through it another way. Many crystals like calcite and quartz bend light differently depending on orientation, and some can even split a beam into two. And once matter is ordered like that, it can start coupling different forces together. One such example is piezoelectricity. When you deform certain crystals, you shift charge distribution inside an ordered lattice, and that shift produces a measurable voltage. In other words, pressure can produce an electrical output. Some crystals are also pyroelectric, meaning a change in temperature can shift internal polarization and create a voltage as well. So in certain materials, you get pressure to voltage and heat to voltage, where the crystal acts like the translator between the two forces. Additionally, because the lattice is ordered, some crystals can support vibration in a stable, repeating way, almost like a built-in tuning fork. And that is why crystals often show up in technologies where humans need reliable timing, sensing, or conversion between motion and signal. Here, order does not just make something pretty. Order makes something directional, predictable, and coupled to other forces. And that raises this question. If order in a solid crystal can convert pressure into voltage, shape how light travels, and support coherent vibration, what happens when that kind of order exists in something softer? What happens when the material can flow, adapt, and reorganize, but still maintain alignment? That is where liquid crystals enter the picture. A liquid crystal is a distinct phase of matter that sits between a conventional liquid and a solid crystal. A liquid crystal can flow like a liquid, but its molecules still maintain a shared alignment. It creates a directional order that gives it crystal-like behavior without rigidity. In many liquid crystals, the molecules are elongated or asymmetrical, which allows them to line up in roughly the same direction. They are not frozen in place, but they are not randomly orientated either. Physicists call this orientational order, and it is what gives them their unusual behavior. There are different kinds of liquid crystal phases. In nematic phases, molecules share a common orientation but are not arranged in layers. In smectic phases, they align and also organize into layered structures. In cholesteric phases, the alignment twists into a helical pattern through space. You do not need to memorize those categories to understand the deeper point, which is that these are stable, measurable states with specific properties. Just like a regular crystal, the material behaves differently along different directions. But because the molecules can still move and reorganize, the material remains soft and dynamic. It can deform, it can flow, it can adapt. It is that combination, order without rigidity, that makes liquid crystals so interesting as we are about to see. When molecules share orientation or alignment, an external field does not just push on isolated particles. It interacts with a coordinated system so that a small influence can reorganize a much larger region. Electric fields can rotate the aligned molecules. Magnetic fields can also bias their direction. Mechanical stress can shear or realign domains. And temperature can shift the material from one ordered state to another. Many liquid crystals are birefringent, so light behaves differently depending on how it travels through the aligned structure. Small shifts in orientation can create big optical changes. Electric fields, magnetic fields, flow, pressure, and temperature, these all can shape orientation, sometimes even changing the type of ordered state the material supports. Because the molecules here can rotate without the structure shattering, gentle inputs can reshape large regions. Liquid crystals naturally form patterns. They break into sections with different orientations, and where those domains meet, defects appear that stabilize lines, spirals, and texture in an otherwise fluid material. Engineers even use some liquid crystal materials in organic electronics because aligned order can support semiconducting behavior, where charge transport becomes more directional when the molecules line up. Taken together, this is what makes liquid crystals so unique and unusual. But now, how does this relate to life? And where in the body do we actually use this state of matter? The answer is not one exotic location. Every cell in your body is wrapped in a membrane made primarily of phospholipids. These molecules have a water-loving head and a water-avoiding tail. And when placed in water, they spontaneously arrange themselves into a bilayer. But that bilayer is not a chaotic soup. Under physiological conditions, it exists in a liquid crystalline phase. The membrane can shift between more ordered and less ordered phases depending on temperature and composition. And those phase transitions affect how proteins function and how signals propagate. This is important because the membrane is where cellular voltage is maintained. The resting membrane potential is not floating in empty space. It is embedded in a liquid crystalline matrix. So when electric fields arise across membranes, they are not acting on an already ordered interface. Here, the boundary of every cell is already a structured, field-sensitive surface. Inside each cell, there is another level of order. The cytoskeleton is made of filamentous proteins like actin and microtubules. These structures are constantly remodeling, yet they maintain alignment and directionality. Microtubules, in particular, form long, polarized filaments that help determine cell shape, intracellular transport, and spatial organization. Although the cytoskeleton is not a static crystal, its aligned polymers create anisotropic properties within the cell. Forces applied to one region can be transmitted along filaments. In short, the cell's interior is not a bag of randomly diffusing components. It is structured and directional. When you combine membrane alignment with cytoskeletal alignment, you begin to see a pattern. Order exists at the boundary and inside the cell, creating a coordinated, responsive architecture. Further into the cell, the informational molecule of life is also an organized structure. When DNA is densely packed, it can exhibit liquid crystalline ordering. In sperm cells and certain viral capsids, DNA strands align in organized helical patterns that resemble cholesteric phases. That means genetic material is not just floating around in solution. Its physical arrangement follows rules of alignment and geometry, and those arrangements can influence accessibility, mechanical properties, and interactions with proteins. Move outward from the cell, and you encounter collagen, the most abundant protein in the human body. Collagen fibers assemble into highly organized, aligned structures that give you tendons, ligaments, fascia, and even the cornea in your eye. Under polarized light, collagen-rich tissues show birefringence, which is one of the classical optical signatures of an ordered material. Collagen fibers bundle, orient, and transmit force directionally. This means mechanical stress does not spread randomly through connective tissue. It travels along lines of alignment. When we talk about posture or tension, we are talking about signals moving through aligned biological material. Collagen-rich connective tissue can also behave as electromechanical materials. Collagen is piezoelectric, meaning when aligned collagen fibers are strained, their internal charge distribution shifts and electrical polarization can appear. In living tissue, that electrical response can combine with fluid and ion movement. But the key point is simple. Deformation in connective tissue can couple to electrical change. So mechanics and electricity are not separate in the body. And around membranes, proteins, and aligned fibers, water is not quite the same. Near surfaces, the first layers of water have altered dynamics and constraints, which means the local environment in biology is more structured than we usually picture. So when you step back, these are not isolated curiosities. Membranes, collagen networks, cytoskeletal filaments, densely packed DNA, and interfacial water all show degrees of alignment and structure behavior that resemble liquid crystalline phases. And if much of our biology lives in aligned, direction-dependent, field-sensitive states, then the convergence we have been building towards feels connected. Electricity, magnetism, vibration, and light, they are not acting on a featureless soup. They are interacting with structured biology. If any of these topics I'm about to touch on feel new to you, I have videos on the channel that go deeper into each one. But the core convergence here is this. Bioelectricity is not happening across an empty boundary. Voltage is maintained across membranes that already have orientation and structure. So electrical conditions meet an interface that is not neutral. Mechanical force is not disappearing into a uniform material. In aligned tissue, stress and strain travel along architecture, and vibration becomes a real input shaped by geometry. Magnetism becomes interesting for the same reason, because fields are meeting organized matter with direction and purpose. And here, the light changes too. Biophotons, which are ultra-weak photons, may behave differently in this ordered material. We saw earlier how liquid crystal structure is known to reshape scattering, polarization, and pathways. Electricity, vibration, magnetism, and light stop feeling like separate topics and start pointing to one underlying reality. Life is organized matter, and that organization may be what lets the body couple to its environment as a coherent whole, which makes the next section a speculation inevitable, at least for me. Because for thousands of years, people have returned to the same idea. The body is an instrument. It is not only flesh and chemistry, but a living system that carries force and sensation with rhythms, pathways, and a baseline state that can shift. When it feels aligned, life feels clearer and more connected. But when it does not, everything feels noisy and heavy, like the instrument is out of tune. In the modern world, the vocabulary may change, but the theme is ancient. We use words like chi, prana, meridians, chakras, and kundalini, alongside newer words like energy, frequency, coherence, and alignment. These words all point to a shared idea. The body is not just a biochemical machine, but a system structured enough to interact with fields and organized enough that certain practices can shift the state of the whole. Breathwork becomes a way of moving the current. Meditation becomes a way of creating coherence. Yoga becomes a realignment of one's inner geometry, and sound becomes entrainment. And the wild possibility is that what people have been calling energy for centuries is not a metaphor at all. It could be the felt side of organization, the subjective experience of coherence, moving through a living, liquid, crystalline body. So here is where we land. Since the body contains liquid crystals, we are not bags of chemistry reacting blindly to the world. We are structured fluids, aligned matter, a living architecture that can hold order and shift. That alone is astonishing. But today, it also opened a door that electricity, magnetism, vibration, and light are not foreign forces acting on something inert. They are influences interacting with a medium that is already organized in ways that can respond. The body seen this way expands science into territory we are beginning only to articulate. And whether you follow that thread into collagen and fascia, voltage maps and regeneration, or magnetism and subtle field effects, the core insight remains the same. Life may be less about what matter is made of and more about the patterns it can hold, the signals it can carry, and the way alignment transforms chemistry into organized form. Thank you so much for being here today. I hope you all have subscribed, liked the video, set your notifications, and just as important, let me know what you think about this and everything we talked about. I can't wait to hear your thoughts. Until next time, take care.